So, as we have our derivative formulas, what we're also going to have is antiderivative formulas. So the notation we're going to use is that if we're taking the indefinite integral of little f of x dx, that's going to be equal to capital F of x plus c. So this capital F of x is representing the antiderivative function. And then we'll just always have that plus c because we'll be able to add on a constant for these. Okay, so constant multiple rule. If we have the antiderivative of k times little f of x dx, where k is a constant, what we're going to have is we'll keep that constant multiplying, but then where we have little f of x, we're going to replace that with the antiderivative function, so capital F of x, and then we'll have a plus c. So this just tells us if we have a number multiplying out front, it keeps multiplying out front. Really what we're focusing on is the function part for taking the antiderivative. If we have the antiderivative of two functions adding to each other, we keep the addition and we just take the antiderivative of each function. So if it's little f of x plus little g of x, we would have the antiderivative function, so capital F of x plus capital G of x plus c. So just take the antiderivative of each, and we would keep addition, subtraction between each of them. Okay, our power rule, which we used on that previous page. So the idea is that we're going to, if we have x to the power of n, when we take the antiderivative, we're going to have x to the n plus 1. So we're bumping up that exponent by 1. But then also we need to divide by that same exponent of n plus 1. So we end up with x to the n plus 1 in the numerator, and then divided by n plus 1 in the denominator, and a plus c at the end there. Exponential functions, if we're taking the antiderivative of e to the x dx, e to the x just stays the same. So it works in both directions, taking the derivative or the antiderivative. It just stays e to the x, and then we'll have a plus c when we take the antiderivative. If the base is not e, so if we're taking the antiderivative of a to the x dx, then what we will have is we'll keep the exponential part, so we'll have a to the x, and when we took the derivative, we would be multiplying by the natural log of a, but now we're going to be dividing by the natural log of a. And then plus c. So we'll have a to the x in the numerator, natural log of a in the denominator, and then plus c on the outside. And then our last rule that we'll want to have down is taking the antiderivative of x to the negative 1, or in another format of 1 over x. So this is going to link to our natural log. So we're going to use the natural log of x. But one little twist here is that we're going to be using the absolute value of x. Just with how these functions work, we're going to need to keep x positive in order to evaluate that natural log because we can't plug in negative numbers. So if we're plugging in a value for x, it can be negative in this 1 over x format, but it cannot be negative in this antiderivative format. So if we were plugging in negative 2, it would work in 1 over x, but it would not work in the natural log. So to get it to work, if we take the absolute value, then it would switch it to a positive 2, and then we could evaluate that natural log. So just a little special thing we need to do there. If we take the antiderivative of 1 over x, it'll be the natural log of the absolute value of x, and then plus c. So those are the rules we're going to focus on. So let's try this out with a few examples down here. So our first one, antiderivative of 2x to the 7th power plus 15 square root of x minus 14 over x squared dx. So I'm going to do is rewrite this all with powers. So 15, instead of square root of x, I'm going to write x to the 1/2. Minus, and then instead of dividing by x squared, I'm going to have 14 times x to the negative 2, and then dx. All right, so applying those power rules. So the constants that are multiplying, the 2, 15, and negative 14, they just keep multiplying. So I'm going to keep the 2, And I'm going to have x to the 7 plus 1, which is 8, over 7 plus 1, which is 8. Plus, that 15 keeps hanging out. We'll have x to the 1/2 plus 1, so x to the 3/2, divided by 3/2. And then minus 14, x to the -2 plus 1, which is -1, over -1. Plus c at the end. And then we can simplify. So 2 over 8, that's a 1/4. So I'm going to go 1/4 x to the 8th power. Let's see, if I multiply by 2, that would be a 30 over 3, so that's 10. So plus 10 x to the 3/2. I'm just going to change that to square root of x cubed. And then dividing by a -1, that'll make it a positive 14. And then over x to the power of 1 plus c. Okay, our next one, the antiderivative of e to the x plus 12 minus 16 over x. So with this, e to the x just stays the same. So we have e to the x, where we have just plus 12. If we just have a constant, we're just going to be multiplying by our variable. So where we have plus 12, that turns into plus 12x. Really, it's like we have 12x to the 0 power. So we're going 0 plus 1 gives us that power of 1. And dividing by 1, so we are using that power rule, but you can just get used to if you see a constant, it gets a variable. And then 16 over x, so if we have 1 over x, that's going to be our natural log of the absolute value of x, and then plus c. And there's nothing else to add on there, so that'll do it. All right, this one here, we have the antiderivative of 8/5 times x to the 1/5 plus 3 to the x dx. So we'll have 8/5 times x to the 1/5 plus 5 over 5, so 6/5. And then in the denominator, where I kept the 5 down there, I'm going to multiply that by 6/5. And then plus, so the derivative of an exponential function, in this case base 3, we would keep 3 to the x in the numerator, but then divide by the natural log of the base of 3, plus c. And then we'll just simplify. So those 5's cancel out, so this is an 8 over 6. So divide both by 2, that'll be a 4/3. And then x to the 6/5 is 5 root x to the 6th. And I'll just keep that plus 3 to the x over natural log of 3 plus c. All right, the last one here that I want to go over is a case where we could find the value for c. So find capital F of x such that the derivative is equal to e to the x. So we want to take the antiderivative of e to the x dx, given that our antiderivative function has this relationship that f of 0 is equal to 10. So we're finding our antiderivative function by taking the antiderivative of e to the x. So if we take the antiderivative, we'll have e to the x plus c. But then what we can do is plug in output of 10 equals e to the input of 0. So e to the 0 power plus c, which is 10 equals 1 plus c, so c is equal to 9. So what that gives us is an exact function. F of x equals e to the x plus 9. So instead of c, we can have an actual value there, and then we could actually graph this. So the derivative function is going to be e to the x, but we have this relationship of a coordinate that our original function is going through.